Welcome to the Data Science Training in Causal Reasoning. My name is Walter Leite and I'm a professor of Research and Evaluation Methodology at University of Florida. I specialize in causal inference with data collected for virtual learning environments. In this course, we will go over the theoretical underpinnings of causal inference, and in other videos I will talk about some specific methods for causal inference, such as propensity score analysis and regression discontinuity designs. So in this first presentation, we'll cover some of the theories that support causal reasoning with observational data. Some common designs for education research include experimental, quasi-experimental, single case, and non-experimental or correlational designs. Experimental designs provide the strongest basis for causal inference because individuals are randomly assigned to groups, which controls for confounding. We'll go later in more details about why that is the case. Now, experimental designs also have a direct manipulation of conditions, meaning that the researcher is in control of the experience that the treatment group is receiving. Now, quasi-experimental designs are weaker than experimental designs with respect to causal inference because there is no random assignment to groups. There could be direct manipulation of conditions, but strong causal experimental design will have a baseline equivalence between treatment and control groups. So the baseline equivalence is the defining characteristic of a quasi-experimental design because it tries to control for selection bias. Now, single case designs is a study where you are focusing on small groups. There is no random assignment, but there is direct manipulation of conditions. Single case studies can support causality, but they don't have very strong external validity. So they focus on not in generalizing, but in evidence of causal inference, for causal inference. Now, non-experimental or observational studies, also known as correlation studies, are the weakest designs with respect to causal inference. In this design, no assignment to groups is possible, and there is no direct manipulation of conditions. Individuals are just observed. The extent that causality can be supported depends on the specific controls that are added in the model to estimate relationships between the treatment and the outcome. Experimental designs in educational research come in different flavors. These are some common designs: the single-level randomized controlled trial, where individuals are not clustered and treatment assignment happened at that level. The multi-site randomized controlled trial is where individuals are clustered, such as students are clustered within schools, but assignments at the student level. So here, multi-site refers to schools. Therefore, it is like the experimental study is being replicated at each school. Now, cluster randomized trials decides where treatment assignment happens at the cluster level, not at the student level. And a common one is students nested within schools and treatment assignment at the school level. Also, common one is students nested within classrooms and treatment assignment at the classroom level. You can have a 3-level cluster randomized trial, students nested within classrooms, within schools, with assignment at the school level. The relationships investigated by a researcher interested in causal inference can be direct relationships. Here we show an example of alcohol consumption leading to loss of motor skills. An indirect relationship, which is what mediation analysis is targeting. So here, alcohol consumption leads to loss of motor skills, which in turn leads to car accidents. Now, a spurious relationship is not causal. A spurious relationship is a relationship that's induced by a common cause. So here, there's a classic example. Ice cream consumption is related to accidents of drowning, but that is temperature, which high temperatures lead to more ice cream consumption and also leads to more swimming, which in turn leads to more drowning. So there is no causal relationship between ice cream consumption and drowning. So you cannot infer any causal relationship from a correlation. So this demonstrates the statement that correlation does not imply causation. So here to the left, we have a correlation matrix that shows a positive relationship of 0.56 between V1 and V2. And here to the right, we have a path diagram showing the actual relationships. So what's happening here is that V1 has zero causal effect on V2. However, V1 is correlated with V3, and V3 has a causal relationship with V2. So V3 is a confounder and provides a backdoor path for a relationship between V1 and V2, because the relationship can go, through this double-headed arrow and through this arrow here, which results in a correlation of 0.56. Here is just the product of 0.7 and 0.8. So this demonstrates that you cannot infer causality from correlation matrix. This shows in a more schematic way what's going on and the difference between correlation and causality. So here, the treatment has a direct causal relationship with the outcome, which is the middle straight arrow. It also has an indirect relationship to the mediator. However, these relationships are also confounded by a true confounder, which is a common cause of the treatment and the outcome. This means that this confounder has an effect on the selection mechanism for treatment, so it influences who receives the treatment. And it also has a causal effect on the outcome, so it influences the outcome. Now, there are a couple more variables here that do not cause problems. Treatment predictors are variables that influence receiving the treatment, but if they are unrelated to the outcome, they don't provide a backdoor path for a spurious relationship. And then outcome predictors just related to the outcome, they also do not provide a backdoor path, causing confounding between treatment and the outcome. When educational research is designed, there could be different targets. Causal description is to try to identify causal relationships. Most educational research is concerned with causal description. Causal explanation is to identify the mechanisms by which a cause leads to an effect. Mediation analysis is concerned with causal explanation. because it is investigating the mediating variables between the treatment and effect. So here's an example. So Math Nation is a virtual learning environment available to all students in Florida. It aims to prepare students to pass the Algebra 1, of course, exam, which is an exam required by the state. It's integrated with the school district, so students can log in with their user ID and password. The treatment here is whether a student uses Algebra Nation. So it's a binary treatment, so you can have the treatment group are users of Algebra Nation, control groups are not users. The correlational question is, does student use of Math Nation relate to increased Algebra and, of course, exam scores? A causal question would be, how does Algebra Nation use affect Algebra 1 AOC scores? And for that causal question, the causal effect is the effect of Algebra Nation use on Algebra 1 and, of course, exam scores. The Shadish-Cooke-Campbell framework that is clearly described in their 2002 book on quasi-experimental designs provides a way to think about what are the pillars supporting conclusions about causality and or conclusions about from educational research in general, and the threats to these conclusions. So their framework comprises of 4 domains of validity: statistical conclusion validity, internal validity, construct validity, and external validity. Statistical conclusion validity refers to the question, is there a relationship between 2 variables? So at that level, the inference is not causal, just about relationships. Internal validity is about the causal question. So is the relationship between 2 variables causal? Construct validity is about whether the particular constructs are specified in a way that they represent the constructs of interest. So what are the particularly causal constructs involved? Are there operationalizations of these constructs adequately representing the constructs? And then external validity is about whether the relationship generalizes across personal settings at times. So it's about generalizability. So here I will just focus on internal validity and construct validity because those are the most pertinent for causal inference. So internal validity is the validity of statements about causal relationship. It is stronger in experimental designs, so it's stronger because experimental designs can control all sources of confounding. Now it's weaker in quasi-experimental designs and even weaker in correlational designs. Now, in quasi-experimental designs, you can strengthen the internal validity by controlling for confounders and demonstrating that important confounders have been included. These are threats to internal validity discussed by Shadish, Cook, and Campbell. History is when something takes place between pretest and post-test. So if, for example, the treatment group experiences challenges in using a certain software that is part of the treatment, but the control group doesn't, that will be history. Maturation is related to biological growth. It's relevant particularly for research with children. It could be, for example, related to language development, where you could have treatment group have a different development than the control group. Testing refers to participants becoming familiar with assessment, and it's particularly important to think about this threat with repeated assessments if you are using similar scales or the same scale over time. Instrumentation is related to assessments not being equivalent. So you could have differences, for example, where you have questions that relate to the construct differently for male and female students, and if you have an unbalance in proportion male and proportion female across treatment and control groups, instrumentation would cause problems. It could lead to bias in treatment effect estimates. Statistical regression has to do with regression to the mean. If you have some outliers in the pretest, particularly in one of the groups, like such a treatment group, there could be regression to the mean in the post-test. Selection is the most prevalent of these in terms of problems. It is when the selection mechanism is not random, and the reasons that individuals sign up for the treatment or participate in the treatment are also related to the outcome. And then attrition, also very prevalent, is when some individuals drop out of either the treatment or control group, and those individuals are different from those that stayed in the study for reasons. They're different with respect to characteristics that also relate to the outcome. Now, construct validity has to do with making generalization about higher order constructs. In research, you have to make operational definitions of your outcomes, participants, settings, and treatments, and the extent that those operational definitions represent theoretical constructs is your construct validity. So, for example, you could be interested in the construct of mathematics ability, but you can't measure mathematics ability directly because it's a latent variable. So you select a set of items to measure mathematics ability. Now that set of items may be unreliable, may be overrepresent or underrepresent the construct. They may have poor construct coverage. So maybe, for example, for mathematics ability, you only have algebra items, but not geometry. So it would be a problem. Construct validity of participants is the extent that your definition of participants represents the construct. So, for example, your intervention may be for students that have ADHD, but there could be problems in the way you classify the students as having ADHD, and the students you have in your sample may not be valid as representing those students that have ADHD. Settings is for the situation of that where your study is. So, for example, your study could be about using virtual learning environments, but virtual learning environments have such a large variability. The virtual learning environment or the environment you are using may not be an accurate representation of the theoretical definition of a virtual learning environment. And treatment would be the theoretical representation of the treatment itself. So, for example, you may be interested in hints as the effects of providing hints in a virtual learning environment, and the operationalization of hint may not match the theoretical definitions of hints. Now, for construct validity, There are several threats. I'm summarizing here from a discussion from a paper by Huggins Manley. These threats were originally presented by Shadish, Cook, and Campbell. So mono-operation bias is when a single operation is used to infer a construct. So, for example, it's common in educational research to measure teacher job satisfaction with just one question. That asks how satisfied are you with your current job, and that would be a mono operation result to potential mono operation bias. Now, mono method bias is related. Is when you just use a single method. So, for example, if you are only using computer logs to measure a construct, you're using a single method. If you're using just surveys, but like so, for example, if you are measuring with computer logs and surveys and observations, then you are reducing mono-method bias because now you have multiple methods. Inadequate explication of constructs where the construct is not defined appropriately. So, for example, in measuring mathematics ability in a virtual learning environment, you may have an assessment that underrepresents the construct of mathematics ability. For construct confounding, you could be measuring mathematics ability, but you could also be measuring reading ability. You could be measuring mathematics anxiety, that or even social desirability bias. So those are confounding constructs that are affecting the scores in your assessment. Unreliability of the scores means that there is extraneous random error. And it's important to keep in mind that the reliability is the property of the scores and is related to the test situation. So the same assessment can be used with some participants in a test situation and provide reliable scores, but in a different test situation provide unreliable scores. Now, in data science, reliability can be challenging because if you're using log data, there are database recording errors. So you could have, for example, recordings of logins that are not reliable because the system never logs off the participants or logs off participants after a month, right? So you can't assume that because the computer made the recording, it's reliable. Now, confounding constructs with facets of constructs. So it would be where you have a limited range, measure a limited range of the construct. So for virtual learning environments, if you were just using logs, there could be engagement with the material through face-to-face discussions, or someone could have printed notes from the virtual learning environment. Treatment diffusion is when elements of the treatment influence the control group. This is a problem, for example, if you do treatment assignment within classrooms, and some students are using, for example, intelligent tutoring system, others are not, but they're sharing notes, they are discussing, and information is passing about the treatment from the treated to the control group. And reactivity to the research situation is when participants' perceptions affect the construct. So, for example, this could be related to the implementation of a teacher professional development, where the way that, for example, it's mandated could create strong reactions for the teachers in a way, not wanting to participate. They may want to game the system when they are participating, which would create customer validity problems for that professional development. When thinking about causal inference, Rubin's causal model is very important. Is a way to understand the quantities you estimate in research aiming at causal inference. So Rubin's causal model is also known as the potential outcomes framework. It states that all individuals have potential outcomes in the presence and absence of treatment. However, only one of those outcomes is observed. So here, for example, if you can say participants have a potential outcome if treated, so z equals 1, it's the treated, and y1 indicates that's the potential outcome if treated. And the potential outcome if not treated for participants is y0. So it's the potential outcome if not treated for those that were treated, which is z equals 1. And same thing for non-participants. Y1 is the potential outcome if they had participated in the treatment, but they didn't. And y0 is the potential outcome for not participating in the treatment, which is observed. So the diagonal here is observed, but the off diagonal is not. So causal inference is a missing data problem where you are using the outcomes that you observe to represent, or you could say impute, the outcomes, the potential outcomes you did not observe. So the average treatment effect is defined based on individual treatment effects. So the individual treatment effects is the difference between the outcome for an individual in the presence of treatment and the outcome in the absence of treatment. Now, this is not observed like because individuals are just assigned to one condition, therefore you can not observe both outcomes. So in theory, the average treatment effect is the difference between the expected values of the outcome for individuals in the treatment and treated and untreated conditions. Okay. Now you cannot estimate it this way because, as I showed in the previous slide, we have a missing data problem, so that not all potential outcomes are observed. These in conventional estimation of average treatment effect, the estimator is the difference between the sample mean of the treatment group and the sample mean of the control group. Now, whether this estimator is valid depends on the design. It is valid in randomized designs, so experimental designs, because the expected outcomes, the expected value of the outcome in the presence of treatment for the treated group is equal to the expected value for the treatment condition for the control group if the control group had been treated. In other words, even though the potential outcomes in the treated condition for the control group are missing, the outcomes for the treated group represent all potential outcomes. Therefore, the mean of the treatment group is an unbiased estimate of the expected value of the outcome in the treated condition for all participants. And similarly, for the control group, the expected value of the outcome in the control condition for the control group is equal to the expected value in the control condition for the treatment group. Therefore, the sample mean of the control group is an unbiased estimate of the expected value for the potential outcomes. So the previous slide shows that a biased estimate of the treatment effect with just a difference between means of the treatment control group requires statistical equivalence of treatment and control groups, meaning that the expected value of one group in one condition is equal to the expected value of the other group in the same condition. And this statistical equivalence can be obtained with random assignment. Now, random assignment is the best way to obtain statistical equivalence between treatment and control groups because they balance both observed and unobserved external variables that could be threats to validity. They maximize within group variability, and if your estimate assumes equal group variances, that makes it terrible. Now, for estimating the average treatment effect, to obtain an unbiased estimate of the average treatment effect, a series of assumptions are required, and I will go over each of these assumptions. So, strong ignorability of treatment assignment, it requires that the distribution of potential outcomes is independent of treatment assignment given covariance. And this is the same as saying that there is baseline equivalence between treatment and control group in all observed and unobserved covariates, so that there is no difference if you did not assign them. The treatment control group would be completely different, completely the same, right? And the treatment control groups are exchangeable, so it doesn't matter which one you would select. The next assumption is overlap or positivity. So it requires that for no participant, there is a probability of 0 or 1 of participating. So nobody's perfectly predefined to participate or not to participate. The stable unit treatment value assumption requires that there is a unique potential outcome for each treatment version. More concretely, it requires that the distribution of potential outcomes for one individual is independent of the potential treatment status of another individual. So one way to understand this is to think that spillover effects, also known as attrition or contamination, violate Sutava. So this happens because if there is spillover effects, the treated and control groups, they interact. So the let's say, for example, that participants in the treatment group are using an intelligent tutoring system and the participants in the control group are not. But some participants in the treatment group are mentoring participants in the control group. So there's a spillover effect. Therefore, the control group is not really the absence of treatment anymore. It is the absence of the direct participation in the intelligent tutoring system, but with mentoring from the participants. So that creates an additional unobserved potential outcome, which would be the outcome when there is mentoring, right? So that is in fact making the potential outcomes of the control individuals a function of the treatment assignment of the treatment individuals. So that's why spillover effects produce a violation of Sutava and result in biased treatment effect estimates. treatment adherence is problematic because it creates multiple versions of the treatment. So let's say your treatment is the use of intelligent tutoring systems for 10 hours. But there are participants that use it for 10 hours. Other participants use it for 8 hours. Other participants use it for 5 hours. So the ones that are using the intelligent tutoring system for 8 hours and 5 hours are not fully complying with the treatment. They are not adhering to the treatment. Therefore, this creates three versions of the treatment. 10 hours, 8 hours, and 5 hours. And that is problematic. Now, you can still estimate a type of treatment effect known as intent to treat, which is not the effect of receiving the treatment, it's the effect of being offered the treatment. So this is used a lot in epidemiology, for example, the effect of offering a vaccine. So in case of intelligent tutoring systems would be the effect of offering the intelligent tutoring system regardless of how much individuals use it. And this is very important for policy. A school district may decide to buy a product that has an effect even if the amount of usage by students varies. So attrition not only generates a missing data problem, but also can generate bias if individuals that stay in the treatment are systematically different from those that leave for reasons that relate to the outcome. So, for example, if it's a intervention aiming at math ability, if individuals with low pre-existing math ability, low baseline math ability, are more likely to leave the treatment, that would cause bias. Now, this can be reduced if you can model the mechanism for attrition. So, for example, if you had in a situation where individuals with low ability are leaving more frequently, if you have a measure of ability and you control for that, you would be controlling for that source of attrition bias. Now, it's also common, I already explained estimating the average treatment effect and the definition of average treatment effect. It's also common to estimate the average treatment effect on the treated, which is the difference between the expected value of the treated in the treatment condition and the expected value of the outcome for the treated in the control condition. This is in experimental designs, the average treatment effect of the treated is equal to the average treatment effect because the treatment and control groups are exchangeable. But in quasi-experimental designs, you can have an average treatment effect of the treated that's different than the average treatment effect. Here I have some references that are cited. The paper by Hughes, Manley et al. Goes over multiple examples of threats to construct validity with an example for virtual learning environments. Rubin's commentary here clarifies targets of causal inference, and the book by Shadish, Cook, and Campbell details internal validity, external validity, construct validity, and statistical conclusion validity.